Hello, welcome to this presentation where we will talk about how a state machine architecture based controller can simplify the process of developing digital power supplies. Here is the agenda. We will begin with a short review of the different tasks that a power supply performs and analyze the challenges involved in implementing them digitally. Next, we will take a look at the different types of controllers that have been used to implement power supplies and introduce how a state machine-based device architecture is differentiated with respect to the other approaches that have been used in the past. A state machine-based controller from Texas Instruments' digital power portfolio, the UCD3138 device, will then be introduced and discussed in detail. Examples of how the most common power supply topologies can be easily implemented with unique value-added features will be presented to illustrate the simplification of digital power using the state machine architecture. Let's begin. What is a power supply? A power supply is a piece of electronic equipment that connects to an energy source and does the task of providing a very well-regulated voltage, current, or power to an electronic load. For example, the energy source in question could be the AC outlet in the wall, and the power supply, an offline AC to DC power supply, which delivers a regulated DC voltage to a data center. Another example, the energy source could be a battery, and the power supply, an isolated DC to DC telecom module, which does the same to a telecom network. Next, if we take a look at what goes on inside the power supply, there are two basic kinds of tasks. On one hand, there is the basic power supply control task, which involves delivering the regulated voltage, current, or power in a safe manner to the electronic load. And on the other hand, there are the housekeeping and system communication tasks. These involve functions such as thermal management, fan speed control, enabling special operating modes to improve the performance of the power supply in special conditions, telemetry, and communication with a host MCU that is outside the power supply. The tasks described earlier can now be thought of as either high-speed or low-speed functions depending upon the time budget available for the power supply controller to execute these tasks. The high-speed functions are those which are repeated at several hundreds of kilohertz inside a modern-day power supply and hence a time budget of just a few microseconds. Typically, this would be, for example, the voltage regulation, which involves the feedback loop control and transient response, cycle-by-cycle protections such as overcurrent protection, and dynamic switching between different states of the power supply. The low-speed functions, on the other hand, have a time budget of several milliseconds or higher. These might be communicating with the host MCU, temperature sensing and fan speed control, and current sharing between multiple power supplies which are all parallel in the same system. The key point to recognize here is that a power supply controller has a formidable task of simultaneously managing different power supply functions, each of which have a different level of urgency and a different time budget associated with them. In a traditional power supply, the tasks described earlier were managed using dedicated controllers. A dedicated analog power management controller was available to take care of all the high-speed power supply functions, while a general-purpose MCU was available for housekeeping and system communication. However, with digital power supplies, the holy grail is having a single unified digital power controller that would have the capability to manage both these functions, both the high-speed and low-speed functions at the same time. Let's now take a step back and look at the evolution of controller architectures for power supplies. Over on the left-hand side, we have the analog controllers used in traditional power supplies that we just spoke about. These are simple devices, can be used for designing power supplies with fast time to market and also deliver high power supply bandwidth. On the other hand, being application-specific devices, these tend to be fixed function and cannot be used as a platform solution for implementing different power supply topologies and architectures. Also, they need many external components for implementing specialized functions and fault protections, And finally, as mentioned earlier, they need a dedicated general purpose MCU for implementing all the housekeeping and communication functions needed in the power supply. Coming to the digital controllers, we see three different kinds of products in the market. Over on the right hand side are the processor driven digital controllers, where a software running on a DSP or a high performance MCU is tasked with executing all the high speed and low speed functions of the power supply. These are very flexible solutions, can be used as a platform device for implementing different control architectures, and since everything is implemented in software, they can be used to support complex control algorithms. Also, the availability of the processor helps to implement housekeeping and communication functions. However, because the software has to necessarily manage all the high speed and low speed functions, the software has to be very carefully architected. This involves more development effort. Secondly, the processor's computation bandwidth is the most important consideration when it comes to delivering the power supply bandwidth. A faster processor, which is able to execute more clock cycles in the same period of time, will be more useful in achieving higher power supply bandwidth. And over in the middle, we have what are known as the hardware implemented digital power controllers. These devices employ dedicated hardware state machines to implement the high-speed power supply functions. The biggest advantage of doing this is that the processor is not involved in any of the high-speed functions. As a result, the processor's computation capability is not a concern for the power supply bandwidth. There are two kinds of devices when it comes to these digital controllers based on state machine hardware. On the left-hand side, we have these fixed function devices which are not programmable but are GUI configurable. What this means is a GUI can be used to adjust and tweak certain parameters of the controller. The benefit of these devices is there is no firmware development involved in the power supply design. On the other hand, being fixed function, these don't lend themselves for platform implementation. And additionally, while some of these devices might have some communication features incorporated, they don't lend themselves for all the housekeeping requirements of most digital power supplies. And finally, we have the category of hardware state machine based devices which are fully programmable and also feature an integrated MCU. As we shall see soon, these devices are architected with some specific hardware power peripherals that can be easily and quickly configured to implement different power supply topologies and architectures. As a result, they are flexible devices and they can be used as a platform solution. There is an element of firmware development in being able to use these devices, but as we will see soon, that primarily involves programming some register sets. Being state machine based devices, there is no concern of power supply bandwidth. And finally, the availability of an integrated MCU allows power supply designers to implement a wide variety of housekeeping functions using this device. On the flip side, there is a learning curve involved for power supply designers when it comes to becoming familiar with the hardware peripherals in this device. And secondly, the ability to implement complex control algorithms is somewhat limited by the hardware peripherals that are architected inside the device. The firmware development task for a processor-based digital controller has several deep considerations, foremost of which is there enough computation power available for designing this power supply of this stated switching frequency and bandwidth? Taking an example of a 50 MIPS CPU for designing a 200 kHz power supply with at least 20 kHz bandwidth, it turns out that only about 2.5 microseconds is available for the key compensation calculations which needs to be completed every switching cycle. This means only about 125 instructions are available for this function. So the question arises, is this enough? Things can get further complicated if there are nested loops or independent control loops which need to be controlled, for example, in a dual output power supply. Next come questions such as, should I use the interrupt or not? What tasks to include in the interrupt loop and what tasks to put in the background loop? And then what task to prioritize when multiple time critical tasks all need to be managed at the same time. Prioritization is absolutely necessary. So how many priority levels are available in the device architecture? Finally, the fastest functions may often need to be coded in assembly language for resulting in a tight code that can be efficiently processed by the processor. This involves further challenges because of lower level programming considerations. In summary, the switch mode power supply hardware and firmware design becomes more intricately intertwined with a processor-based controller. The firmware development also becomes more of an involved process with a processor-based digital controller. After this discussion, it should be pretty clear to the audience that the category of programmable state machine-based controllers with the integrated MCU possesses certain unique advantages and represents a very attractive compromise over the other categories of digital controllers. With that, let's now take a look at a device from TI's digital power portfolio, the UCD3138, which belongs to this category. Pictured here is a simplified high-level block diagram of the UCD3138 digital controller. The device consists of two portions. The top half represents the programmable hardware state machine, while the bottom half represents a general-purpose MCU. As mentioned earlier, the state machine executes the time-critical power supply functions with no dependence on the processor. The state machine features hardware peripherals that support the most common power supply topologies such as boost BFC, resonant LLC, phase-shifted full bridge, hard switch full bridge, buck, and also other special power supply functions such as peak current mode, burst mode, and so on. Over at the bottom, we have the fully programmable MCU, which is used for configuring and initializing the state machine, and after that, it's primarily involved in running the housekeeping, communications, and telemetry functions of the power supply. Having said that, the MCU is also available for any low-speed power supply functions such as a slow power factor correction, voltage loop control, and current sharing. In terms of benefits, the most important advantage of this architecture is the ease of firmware development. In order to program the state machine, all that the designer has to do is become familiar with the hardware peripherals in the device and assign bit values to specific registers. All the compensation calculations involved in the high-speed loops is implemented in the high-speed state machine hardware, so there is no need for complex time slicing of computation resources between the low-speed and the high-speed functions. A second benefit is that this architecture allows designers to develop high-bandwidth, high-frequency digital power supplies. With no reliance on slower firmware decisions from CPU, it is possible to achieve a very high bandwidth power supply using the hardware state machine. This benefit becomes even more obvious and attractive at high frequencies when the switching period is very short, and so is the calculation time for the CPU. Additionally, when multiple loops, such as a voltage loop and a current loop, need to be simultaneously controlled, or in situations where there are multiple outputs in the power supplies and there are multiple power stages to be controlled, the benefit of this device becomes more and more attractive. Other benefits include low power consumption by the device by way of the hardware state machine and a high level of system integration, because now one device can control both the power supply and also implement the housekeeping and communication functions. In summary, this architecture reduces the entry barriers for designers to develop digital power supplies and enables a fast time to market. Now, let's take a deeper look at the block diagram of the UCD3138 device. Shown on the left here is a picture of the block diagram of the device reproduced from the UCD3138 datasheet. The state machine hardware in the device is confined primarily to the upper half of the device above the dotted lines,
and it includes hardware for controlling 3 simultaneous feedback loops. On the bottom of the device is the general purpose microcontroller, which is a 31.25 MHz 32-bit ARM7 controller, and it also features certain hardware components such as fast analog comparators. Now, let's zoom in to see how the hardware state machine is used to control 3 feedback loops simultaneously. The feedback loop control is accomplished in the UCD3138 hardware state machine using 3 fundamental components. First, there is the front end block, which is the feedback voltage sensing and error generation block. Next, there is the digital compensation block, which involves a 2-pole 2-0 PID style compensator. And finally, the DPWM, or the digital pulse width modulator block, which is responsible for generating the output pulses. This block is capable of pulse width modulation, frequency modulation, and even phase shift modulation. The resolution of the pulses from this block is 250 picoseconds for pulse width modulation and 4 nanoseconds for frequency and phase modulation. With these 3 blocks, it is possible to control a single feedback loop, such as a voltage loop or a current loop. In the analogous world of analog controllers, the front-end block would be similar to the error amplifier. The digital compensation block would be very similar to the compensation pin of an analog controller with the external R's and C's used in the compensation network. And finally, the DPWM block would be similar to the PWM comparator in the analog controller. 3 sets of these fundamental loop control blocks are available in the UCD3138. In addition, a 4th DPWM block is also available for generating additional control signals such as synchronous rectification. Next, in power supplies, it's quite common to send signals from one control loop to another. A classic example is average current mode control, where an outer voltage loop sends a command signal to an inner current loop. In order to achieve these functions, the UCD3138 device has the hardware block known as the loop multiplexer, which allows one loop to be nested inside another. Finally, the hardware state machine in the 3138 also includes specialized power peripherals for implementing some very commonly requested power supply functions such as peak current mode control, constant power, constant current regulation under overload, burst mode for better light load efficiency, automatic mode switching between PWM and LLC modes during startup, fast input voltage feed forward, and so on. Next, let's take a deeper look at the front-end module, which is the sensing and the error generation module in the UCD3138. This block is comprised of an analog differential amplifier, which accepts the feedback signal from the power supply, followed by an adjustable gain error amplifier, whose reference is driven by a DAC. The DAC is programmable from a variety of input sources, such as the ARM7 microcontroller or a different loop in the power supply. Following the error amplifier, we have an extremely high-speed ADC, which is called the error ADC, or the error analog to digital converter, which does the task of digitizing the analog error signal at the output of the amplifier into the digital domain. It is worth noting that in the UCD3138 device, the conversion boundary between the analog and digital domains is at this EADC block. Each front-end module also has a dedicated peak current mode comparator, whose reference is driven by the DAC, through which programmable slope compensation can be implemented. All these hardware blocks are available in each front-end module, and remember, there are 3 such front-end modules available in the UCD3138 device. With this, the UCD3138 device is well positioned to independently control 3 high-speed feedback loops. What's more, the digital hardware in the 3138 device can operate at such high speeds that it can support switching frequencies of up to 2 MHz in the power supply. Moving on to the bottom half of the block diagram, Let's talk about protection hardware in the device. The UCD3138 device has a bank of 7 high-speed analog comparators which can be used to instantaneously turn off any of the DPWM outputs. Thus, these comparators can be used for functions such as cycle-by-cycle current limiting. Following the comparators, there is an advanced fault management block called the fault multiplexer. This block is very flexible and has the capability to accept inputs from a variety of sources such as analog comparators, digital comparators, external GPIOs, and can initiate a response for turning off any of the DPWM modules. This block also has the capability to add some filtering to the output of the analog comparators. This is a sort of a digital filtering. For example, the fault mux block can accept the input from one of the analog comparators and count to a predetermined number of triggers before initiating a response with the DPWM outputs. This concludes the introduction to the hardware state machine in the UCD3138 device. Let's now talk about the MCU. As mentioned earlier, the device features a 32-bit ARM7 processor, on-chip memory by way of program flash, data flash, RAM and ROM is available, multiple communication ports available such as UART, PMBus, I2C and JTAG. And what's really interesting is that this device features a fourth A to D converter. Why fourth? Well, if you recall, this device features 3 front-end modules, and each of these front-end modules has a dedicated high-speed error A to D converter called the EADC. This A to D converter shown in this slide is a fourth A to D converter, which is a slower speed but higher resolution block that can be used for general purpose sensing such as temperature sensing. Finally, the device features other blocks common in MCUs such as timers, captures, and power supply monitors. With that introduction, let's take a look at how the UCD3138 device can be used to control an isolated DC to DC power supply, in this case a phase-shifted full-bridge converter. Over here on the primary side are the 4 full-bridge MOSFETs. Here is a power transformer and the isolation boundary, the 2 synchronous rectification MOSFETs on the secondary side, and the UCD device also sitting on the secondary side, which makes this an example of secondary side controlled digital power supply. In order to regulate the power supply, the output voltage is sensed and presented to a front-end block for voltage loop regulation. The same signal is also presented to an analog comparator for overvoltage protection. For the current loop, the primary side current is sensed using a current transformer and presented to a second front-end block for implementing peak current mode control, and the same signal is also presented to another analog comparator for implementing fast cycle-by-cycle overcurrent protection. Finally, the output current in the converter is sensed and presented to a third front-end block for the purpose of implementing a constant power, constant current regulation loop. This loop takes in effect when the power supply is operated beyond its nominal operating current range, causing the output voltage to fall back and finally shut down when the overcurrent situation is encountered based on the output current. The same signal is also fed to an ADC input for implementing the slow current sharing function using the ARM processor, and optionally the same input can also be fed to an analog comparator for implementing overcurrent protection based on the output current in this power supply. Having made the decision on what control signals will be presented to what hardware blocks, the exercise of programming the digital controller to control this power supply is simply a matter of following the recipe which configures the appropriate registers for delivering the appropriate functions with the controller. In terms of the output, the DPWM modules 2 and 3 are used to control the primary side MOSFETs, while the DPWM modules 0 and 1 are used to control the synchronous rectification MOSFETs on the secondary side. In summary, this is an example where the UCD3138 controller is used to regulate one voltage loop of several kilohertz bandwidth and 2 current loops all simultaneously using the state machine hardware. What's more, the ARM processor in the device is now available for communicating with the system microcontroller using PMBus or I2C, and for communicating with the primary side digital controller controlling the power factor correction block using UART through an isolation barrier. Next, let's take a look at how the controller can be used to control a two-phase interleave boost power factor correction AC to DC converter. In this example, the AC line voltage and the DC bus output voltage are sensed and presented at the inputs of ADCs, which allows the ARM processor to use this information and run them through mathematical calculations to regulate the voltage loop. In addition, an element of the voltage loop is presented into the hardware state machine, which feeds as a command signal for the current loop. The current in the power supply is sensed using current sense transformers and presented to two independent front-end blocks. This allows two front-end blocks and two hardware peripherals to be used independently to control two current loops. The same signal is also presented at the input of analog comparators for providing cycle-by-cycle current protection. In terms of the outputs signals coming from two DPWM blocks are 180 degrees phase shifted to control the two interleave power MOSFETs. Optionally, it is also possible to sense the inductor current using a current sense shunt and present that to a front-end module to regulate a single current loop using the state machine hardware. Of course, in this condition, you would lose the option to have good current balancing between the two current loops. So, in summary, in this example, the UCD controller is controlling two fast current loops of a few kilohertz bandwidth controlled by the state machine hardware. Furthermore, the current loop is nested inside a slow voltage loop which helps to achieve average current mode control. The current loop is implemented in hardware, while the voltage loop, being a slow loop which is typical for power factor correction converters, only tens of hertz crossover frequency, can be implemented using the ARM7 MCU. So this is an example where the ARM7 processor can be used to implement a slow power supply function. Let's take a quick look at a third example, which is a dual output DC to DC converter that's comprised of a half-bridge resonant LLC converter which delivers one of the outputs, and then followed by a downstream buck converter which provides the second output. So here the controller in the power supply has the task of controlling two power stages, one a resonant LLC and another one which is a buck. Keep in mind, both these power stages can be operating at several hundreds of kilohertz switching frequency. In this example, the LLC converter is controlled by one hardware loop, and the output of the buck converter is controlled by another hardware loop. Furthermore, the availability of the third loop gives the option to sense the output current using a shunt and implement functions such as constant current, constant power loop control. So in this example, two voltage loops, possibly several kilohertz and tens of kilohertz bandwidth, and one current loop can all be implemented using the state machine hardware of the UCD3138 device. This is really an example where the availability of hardware to support multiple loops allows a single digital power controller to manage the entire power supply. Up until this point, we have looked at how the controller can be used to implement common power supplies. Now, let's take a look at how the controller can be used to achieve more. Here is an example of average current mode control where the converter moves from CCM to DCM operation based on the load. During CCM operation, the current is sampled at the midpoint of the rising edge of the inductor current. And in this mode, the midpoint represents the average current in the power converter. However, in a DCM mode operation, the same midpoint overestimates the average current in the switching cycle and in the power converter. So, how do we sense and obtain a more accurate average current representation in the DCM mode? That's the problem we're trying to solve. With the UCD3138 controller, the EADC hardware inside the front-end block can be enabled in oversampling mode and hardware averaging mode. This allows the controller to gather up to 8 times the number of samples in the same switching cycle, which can then be averaged to achieve a more accurate estimation of the average current in the power supply. What enables this unique capability with this controller is the high-speed computation capability of the digital state machine hardware inside the device. With 8 times sampling on a 65 kHz switching converter, the sampling rate is greater than 500 kHz, which allows a calculation time of less than 2 microseconds. As mentioned earlier, the digital state machine hardware in the UCD3138 device is capable of operating up to 2 MHz switching frequency. This cool feature can now be conveniently applied in a power factor correction application to achieve very low current distortion and a reduction in ITHD by up to 4%. By engaging the 8x oversampling function in the DCM mode, the controller is able to obtain a better representation of the average current under DCM mode, which can then be matched to the current command inside the controller to achieve very good current shaping in the power factor correction converter. Next, here is another example where the controller helps you to achieve more. Here we are talking about something known as on-the-fly firmware upgrade of the power supply. What this means is uploading and commissioning a new firmware in the power supply without actually shutting down the power supply. The hardware state machine in the device runs autonomous of the processor and controls the power supply. This means if the processor is busy with other tasks, the power supply is still well regulated and protected by the state machine. On the flip side, the state machine running autonomous of the processor frees up the processor for specialized housekeeping functions such as these. On-the-fly firmware upgrade is achieved using the UCD3138-064 device in the same product family. This device is a dual memory bank architecture device. What's unique about this device is while one memory bank is executing the incumbent firmware, it is possible to simultaneously write a new firmware to the other block. The upgrade process is done in a series of systematic steps. First, the ARM processor writes the new firmware into the redundant block, the block 2, while the primary block, block 1, is executing the incumbent firmware and the state machine is controlling the power supply. Then the ARM processor runs an integrity check to ensure the firmware has been written properly, following which the processor stages for a live switch in execution from block 1 to block 2, and finally, when the timing is right and when the variables have been saved, the processor executes a live switch, which then allows the power supply's firmware to be upgraded on the fly. The key benefit of on-the-fly firmware upgrades is it helps IT service providers to reduce downtime in server data centers when the switch mode power supply has to be upgraded with a new firmware for either performance upgrades or bug fixes. Here is a demonstration of the on-the-fly firmware upgrade function in a DC to DC resonant LLC converter. The upgrade in the firmware actually involves the power supply operation. Here, a constant power regulation function is added for overload current protection, and the overcurrent protection in the converter is replaced from an output current based scheme in the incumbent power supply firmware to something that is based on the primary side current of the DC to DC converter. The pictures in the bottom show the waveforms when the power supply firmware is upgraded. A GPIO is made to toggle when the firmware switches, and it's very clear that the output voltage of the power supply and the resonant current of the converter are completely unperturbed. The evidence of the new firmware kicking in is very clear because of the output voltage drooping, because this switch was performed at a condition when the power supply was operating in overload condition. Since the original firmware did not have the constant power function, it continues to regulate at the output voltage, while the new firmware droops the output voltage, showing that the constant power function has taken effect. In conclusion, let's have a quick run through of the key differences between a state machine based controller and a processor based controller. The key high-speed functions such as the voltage and current feedback loop are controlled by the digital state machine hardware. In a processor-based device, software running on the processor controls all the loops. Critical decisions are made without processor intervention, and there are no latencies involved. In a processor-based solution, the availability of a powerful processor or even a coprocessor at times is at the core of every decision that's being made. In a state machine-based device, the support for different power supply topologies quite simply depends on the hardware architected inside the device. This allows for a quick decision-making process for the power supply designer who's trying to identify a controller for his project. On the other hand, with processor-based devices, the power supply designer and the firmware engineer have to involve themselves in detailed upfront calculations to ensure that the processor of choice is able to support the power supply requirements. With a device such as the UCD3138 that is engineered with enough hardware for independently controlling 3 loops, which don't need resource sharing, the possibilities to support many power supply topologies exist. With a CPU-based device, which typically have 1 or 2 data converters and a processor of known capability, the firmware designer and the power supply designer once again have to go through a detailed upfront decision-making process. With the state machine hardware doing the heavy lifting power supply control functions, the processor is fully available for housekeeping, communications, telemetry, and other specialized functions. On the other hand, the processor must be shared between both the power supply control and the housekeeping functions. Firmware development simply involves configuring the state machine hardware for the desired power supply topology and architecting the low speed functions using software running on the MCU. On the other hand, all the desired functions must be architected in software with proper attention to timing and priorities between the high speed and low speed functions. In summary, the state machine based digital power controller that is programmable represents simplification of firmware development, reduced entry barrier, and fast time to market for anyone designing digital switch mode power supplies. I now invite the audience to access ti.com to review the information available about the digital power controller that has been presented today. This includes product data sheets, fully functional evaluation modules demonstrating power supplies controlled by the digital controller, videos discussing on-the-fly firmware upgrades, and documentation demonstrating high-speed functions implemented using this control. This concludes this presentation on digital switch mode power supplies. Thank you for your time.